Hi everyone, welcome back. Let's continue our discussion of electrons in periodic potentials. In the last mini lecture, we talked about some general features of Bloch electrons. We talked about the meaning of the wave vector k. It's not quite the momentum, it's the crystal momentum. We talked about the fact that we can always pick a value of k that lies in the first ρ1 zone. We talked about the implications of that for things like the periodicity of the eigenvalues as well as how we represent them. We also talked about the velocity of Bloch electrons. I stated without proof that we can write it in the following way that's very much analogous to our expectation for the group velocity of a wave. It's the gradient of the energy as a function of k. This is somewhat surprising because it means that in general, Bloch electrons have a non-zero velocity, even in the presence of the periodic potential. This means that it cannot be the periodic potential itself that causes collisions. This is in direct conflict with our expectation from the Drude model, and it's something that we'll come back to again in this course. So let's continue to talk about some general features of electrons in periodic potentials. Just as we did in the Sommerfeld model, we can define a Fermi surface. This is the surface that separates the occupied from the unoccupied levels in the ground state. So the ground state of a system with capital N electrons has the lowest energy levels filled with the N electrons, and any level in energy above that is empty. Again, the surface is the surface that separates the unoccupied from the occupied levels. We can also define the Fermi energy and the Fermi wave vector in ways very much analogous to how we define them for the Sommerfeld model. So there are several different ways in which this filling can occur. So the first way in which this filling can occur is if some number of levels are filled. In general, this is the case. The band gap, we'll say, is the difference between the highest occupied and lowest unoccupied band. So if the Fermi energy lies between bands, if one band is completely full, then we'll say that the band gap is the difference between the highest occupied and the lowest unoccupied band. So for this case, it's helpful to think of these levels really as being bands. So if some number of bands are full, we'll say that the band gap is the difference in energy between the highest occupied and the lowest unoccupied band. When the band gap is of order kBT, the thermal energy scale, the material is a semiconductor. Essentially because electrons can be excited across the band gap. And this is something we'll talk about a bit later in this course. When the band gap is substantially higher than kBt, the material is an insulator. One thing that's interesting to think about here is that, remember, the number of levels per band is equal to the number of primitive cells in the crystal. So here I'm using the term level to refer to a single value of K, an allowed value of K. The total number of allowed values of K in the first Brillouin zone is equal to the number of sites in the crystal. So we'll say the total number of levels per band is equal to the number of primitive cells in the crystal. If we imagine that each level, each single particle level, each value of K can accommodate 2 electrons, one with spin up and the other with spin down. A band can be full only when there are an even number of electrons per unit cell. So one full band requires 2 electrons per unit cell. So one can have an integer number of full bands when the number of donated electrons per atom is, or per unit cell rather, is even. Okay, so that's an interesting feature of band theory. This is true. Insulators have an even number of electrons that they donate to that they donate to conduction per unit cell. Okay. Another case is that some bands may be partially full. In this case, the Fermi energy, as we said before, EF is the energy of the highest occupied level. Okay. Again, as we said before, the surface separating the unoccupied from the occupied levels is called the Fermi surface. We typically think of the Fermi surface as something that occupies K space, as something that occupies reciprocal lattice space. So let's talk about the density of states now. So as we did before in Sommerfeld theory, we often want to calculate things of the following form. We often want to calculate, let's say, the total or the average value of some quantity over different levels and different bands. Often it's the case that we're interested in this quantity Q per unit volume in the limit where the volume goes to infinity. As before, we can express this as an integral over the allowed values of K of this function Q of K. Remember, in Sommerfeld theory, we changed variables from K to energy because often the things we are interested in depend on energy. So most of the time we can say that, or it's advantageous to say that this quantity little q is equal to an integral over energy of the density of states, G of E, times now this quantity Q, which we've written as a function of E. Remember, the density of states is something that describes the number of states per unit volume within the small energy dE of energy E. In the case where we have multiple bands, we'll write the total density of states as the sum of the density of states of the individual bands. We'll say that the density of states of band N at energy E can be written in the following way. This is a little bit of a different definition than we wrote down before. It still has the same meaning. Gn of E dE is equal to 2 over V, 2 over the total volume times the number of allowed wave vectors between E and E plus dE in the nth band. The definition we've written down here is equivalent to this. Here it's an integral over this delta function, and the delta function clicks whenever there is an allowed energy. And so by summing up all of these clicks, we get essentially the total number of wave vectors with energy within a small amount of E. Of course, there's this factor 2 as a result of spin degeneracy. That's why this is a 4 instead of an 8. And the per unit volume has to do with the normalization of the delta function. So let's derive the density of states for Bloch electrons. Another way for us to define G is the following. We can say that the density of states in the nth band at energy E times dE now is just essentially the number of states per unit volume in the small energy window. So we'll write the integral like this. The total number of states in this window dE will be equal to this integral, and we've sort of replaced the delta function with this object, which gives us 1 if there is an allowed energy value within this window. Okay, this is an integral over the first Brillouin zone, the primitive cell of the reciprocal lattice. This is a volume integral, obviously, though dE is rather small. So what we can do is actually treat it as a surface integral and multiply it, if you like, by some length in the third dimension. So let's do the following. So let's define a surface in energy space. So I'm going to call this surface Sn of E. This is the surface of constant energy E in the nth band. This surface is in K space. It's really a three-dimensional surface, but I can only draw very easily a two-dimensional surface. Let's draw another surface. I'm going to call this Sn of E plus dE. This is the surface corresponding to energy a little bit more than E. The total number of allowed states within dE of E is essentially going to be the volume between these two surfaces. So really, of course, I should be doing a volume integral. But one way for me to imagine simplifying this is to say, well, these two surfaces are basically the same. So to approximate this volume integral, let me just integrate over the surface and multiply then by the distance between these two surfaces. So let me define the perpendicular distance between these surfaces as delta k, which is a function of the wave vector k. So again, this surface lives in k space. Both of these surfaces live in k space. The integral we're going to carry out to extract the density of states is a k space integral. So let's say the following, that Gn of E, dE, the total number of states within dE of E, is equal to the surface integral now of delta k of k. So this is a two-dimensional integral in k space. When we're multiplying it by a length in k space, this gives us a volume integral in k space. Okay. Let's now find an expression for delta k, this perpendicular distance between the two surfaces. Well, remember that the gradient of the energy E is normal to surfaces of constant energy. Okay. The magnitude of the gradient of E is the rate of change of E with respect to K. So we can say that E plus dE is equal to E plus the gradient of E with respect to K times delta K, which is this infinitesimal distance in K space. Because the gradient of E is perpendicular to surfaces of constant E, we know that this distance then is the perpendicular distance between surfaces of constant energy separated by dE. So this lets us say that delta K as a function of K is equal to dE over the absolute value of the gradient of E. All told then, we can write down the density of states times dE is equal to the surface integral times dE over the absolute value of the gradient of E. Thus, the density of states at the nth band is equal to the surface integral of 1 over the absolute value of the gradient of E. Okay? This will be important later on in the course. This is the formal definition for the density of states of Bloch electrons in the nth band. For now, let's talk about something called Van Hove singularity. Let me write down our expression for the density of states. Because E is a periodic function, as we discussed in the last lecture, it's periodic in K. There will be values of K for which this gradient vanishes. When that happens, this integrand obviously diverges. It turns out that the diverges are integrable, but nonetheless, they still lead to divergences in the derivative of the density of states. These are called Van Hove singularities. So it's often the case that one will have a density of states for some band that might look like the following. So there are Van Hove singularities at these points indicated by arrows. This is where the derivative of the density of states vanishes. We say that these Van Hove singularities happen when one has flat bands, when the energy of a band does not depend on K. And so these are indeed experimentally verified objects, and it's worthwhile to know. This is one of the important features of bands for Bloch electrons. So in the next mini lectures, we will start to consider some of the effects of energy bands on electrons. We'll consider some of the effects of periodic potentials on electrons. We're going to consider really two cases. The first consists of weakly bound electrons that interact weakly with the periodic potential, and the second case consists of tightly bound electrons. We'll start with the case of a weak coupling first. There are a couple of reasons why you might imagine that that's true. The first is that the Pauli exclusion principle will prevent conduction electrons from getting too close to the core electrons. This will, in some sense, force the conduction electrons away from the core, away from the ions. You can also imagine that electrons can screen the potential associated with the positive ions from other electrons. So these are two hand-wavy reasons why considering the case of weak coupling of electrons to a periodic potential is worthwhile. Since the electrons are weakly coupled to the periodic potential, we'll do perturbation theory. Remember that there are two broad classes of perturbation theory, degenerate and non-degenerate perturbation theory. In the case of degenerate perturbation theory, one generally expects that perturbations will lift degeneracies. And that's exactly what we'll see when we consider this in more detail. We'll also find that degeneracies happen at the edges of the Brillouin zone. These correspond directly to Bragg planes for X-ray diffraction. So when we talked about X-ray diffraction, we found that interesting things happen when the incident X-ray wave vector was equal to half of a reciprocal lattice vector. That same point, half of a reciprocal lattice vector, generally corresponds to the edge of a Brillouin zone. Energy levels are often degenerate at the edge of a Brillouin zone. This is where the coupling to the lattice will lift that degeneracy and create a band gap. So more about this in the coming mini lectures. Stay tuned for more fun with electrons in periodic potentials.